Hello, welcome to the EduSat program. This is the session 2 related to the bending moment and shear force. Previous session we discussed about the basics of shear force and bending moment, and also how to calculate the bending moment and shear force for the one small beam. I have taken one cantilever beam and I explained. This session we will discuss about the different types of problems related to the cantilever beam. What we discussed the previous session, shear force diagram. The diagram which shows the variation of shear force along the length of the beam is called the shear force diagram. Another one is bending moment diagram. The diagram which shows the variation of bending moment along the length of the beam is called the bending moment diagram. We have to draw the shear force diagram and bending moment diagram for the cantilever beam, simply supported beam, as well as overhanging beam. And one more important point what we discussed in previous session, shear force, for calculation of shear force and bending moment we have assumed signs of convention, that the shear force calculation, downward forces we are taken as a positive, upward forces taken as a negative. Normally in beam, simply supported beam, upward force is reaction, downward forces are loads. Loads may be uniformly distributed load or point load. Whatever the downward forces we are considering as a positive sign, and then upward forces we are considering as a negative. Related to the bending moment calculation, clockwise moment we are considering as a negative, anti-clockwise moment as a positive. Let us consider one simple problem. A cantilever beam 4 meter long, it is 4 meter long, and carries in point load 3 kilonewton at free end. In problems there may not be given sketch, we have to draw the sketch. It is a cantilever beam, that means one end is fixed, other end is free. A point is free, B is fixed, and it carries in point load of 3 kilonewton at free end. Okay, after drawing the sketch, to calculate the shear force, first shear force at A. At A, whatever the, here at A we can observe 3 kilonewton is acting. This is the 3 kilonewton acting. That 3 kilonewton has been considered as a shear force. Okay, shear force at A, one point load is there, 3 kilonewton. Then coming to shear force at B. Shear force at B, from A to B no further load is added, therefore it is 3 kilonewton. If it is any load is added, then it would have been increased. Now here only one point load is acting, therefore shear force at A also, B also 3 kilonewton. Then bending moment calculation. Bending moment at A point, force is 3 kilonewton, distance is 0, because we are calculating the bending moment exactly at the A point. 3 into 0, therefore bending moment at A is equal to 0. For cantilever beam, always bending moment is 0 at the free end, maximum at the fixed end. Bending moment at B. Here, for B we have to take the moment from A to B. Moment means it is in this direction we have to take the moment. 3 into 4, because it is a clockwise moment. 3 into 4 it is clockwise moment, therefore minus. We are considering the clockwise moment as a negative, anti-clockwise moment as a positive. Here it is a clockwise moment, minus 3 into 4. 3 is the load, 4 is the distance. 3 into 4, 12 kilonewton meter is the bending moment at B. What we can observe here, two salient points are there, A and B. If any further loads are there, we should have calculated that point also, bending moment. Here only 2 points are there, A point bending moment is 0, B point bending moment is 3 into 4, 12 kilonewton meter. Now we have the values of shear force as well as bending moment. To draw the shear force and bending moment diagram, let us take this here. This is the beam what is given. Okay, then first draw the horizontal line. Then we have the shear force at A 3. You mark the 3 kilonewton upward. This is scale is approximate. Okay, just proportionate drawing you have to draw. Then up to B it is same 3 kilonewton constant because no further load is added, therefore it is a 3 kilonewton. Then join the last point, therefore it is a rectangular, it is constant from the A to B and maximum shear force is 3 kilonewton. Okay, then this is called shear force diagram. Next, for drawing the bending moment diagram, first draw the horizontal line and at A it is 0. This is the point for the A point, and then we have the B point bending moment. This is bending moment calculated as a 12 kilonewton meter. Okay, this we have to mark the 12 kilonewton point here. Draw vertical line downwards, because it is a negative we have to draw the downward. If it is a positive you could have drawn the upward. Then join from the 0 point to A point to B point. This triangular portion is the bending moment diagram. It is a negative because it is a hogging bending moment. This is the shear force and bending moment diagram for the cantilever beam carrying in point load at the free end. Let us consider one more example with 2 point loads. A cantilever beam 5 meter long, span is 5 meter, and it carries in point loads of 5 kilonewton, point load of 5 kilonewton at free end, 5 kilonewton at free end, and 3 kilonewton 3 meter from the free end. From the, this is the free end, this is the free end. At free end 5 kilonewton is acting, and then from the free end 3 meter another 3 kilonewton load is acting. From the free end, sometimes in problem they will give from the free end, or sometimes it may be from the fixed end. You should see the problem what is given. First we have to draw the proper diagram, otherwise entire problem will become wrong. That is why here you have to read properly problem and then draw according to the details given. Here 3 meter from the free end, therefore it is 3 meter from the free end has been considered. Then this is the drawing and you have to mark the salient points. A point, this is the one point load A point, and second point is B fixed end. C is the point where another point load is acting. 5 kilonewton and 3 kilonewton, 2 points loads are acting in this cantilever beam. Let us calculate the shear force. Shear force at A. Now this is the point we are considering here. At A 5 kilonewton is acting. Therefore shear force at A is equal to 5 kilonewton. It is a downward we are considering as a positive. Then shear force at C. What is the value of shear force at C? Here 5 kilonewton plus another 3 kilonewton is added at the C. 5 kilonewton plus 3 kilonewton, total is 8 kilonewton at shear force at C. Next, what is the value of shear force at B? What is the value? Here 5 kilonewton is at A, 3 kilonewton at C. Between C to B no load is added. Therefore, whatever the value of shear force here 8 kilonewton, same will be at the B also. Shear force at B is 8 kilonewton itself, because no further load is added. Therefore, shear force at B is equal to 8 kilonewton. Next, bending moment calculation. Bending moment at A is 0, because for cantilever beam always bending moment at free end will be 0. Force into distance is 0. Bending moment at C, this is the C point. Up to here we have to take the moment. Up to here moment we have to take. Okay, 5 kilonewton into 3 meter distance. Distance is the 3 meter. Moment means force into perpendicular distance. Here force is 5 kilonewton and distance is 3 kilonewton. Minus 5 into 3, because it is a clockwise moment. Minus 5 into 3, minus 15 kilonewton meter. Then bending moment at B. calculating the bending moment at B, you can see bending moment at B, force is 5 kilonewton is acting here, 5 kilonewton into distance up to here, 5 into 5, that is 5 into 5 is the force into distance 25, and another one force is acting here 3 kilonewton, 3 kilonewton into distance, this distance from this point to here distance. What is the distance from C to B? C to B is 5 minus 3, 5 minus 3 is 2 meter. Okay, how to calculate moment at B? 5 kilonewton into 5 and 3 into distance is 2 meter. 3 meter here, from here A to C is 3 meter, balance is 2 meter. This 3 kilonewton is acting at a distance of 2 meter from the B. Therefore 3 into 2 and 5 into 5, that is the total moment. 5 into 5 plus 3 into 2, that is total 31 kilonewton meter is the maximum bending moment at B. To draw the diagram, see, first draw horizontal line, and then here vertical shear force vertical line 5 kilonewton, and then horizontal line, because no load is added from A to C, that is why it is a horizontal line. Then 5 plus 3, 8 kilonewton. Then again no change of shear force from C to B, that is 8, same remains constant. Then close this. Here we can observe step is there. This step is equal to 3 kilonewton. This from here to here, 5 minus 3, 5 minus 8, that is 3 is the difference, vertical drop. This point, this here is the 5, therefore this vertical drop is 5. That means wherever the point load occurs, that point drop will be equal to this force. If it is a point load is 5 kilonewton, 5 drop should be there, 3 kilonewton, 3 drop should be there. This vertical line should be equal to the point load. Here also vertical load is equal to the point load. This is the shear force diagram. Next, bending moment diagram. For drawing a bending moment diagram, first draw the horizontal line, because it is a negative top line, horizontal line. Then we have to mark the points. Here it is 0, this point is 0, and one more, this exactly below this point we have to take a 15, whatever calculated value, 15 kilonewton meter. Then 31 kilonewton meter is the fixed end value. Mark the point 31 kilonewton and 15 kilonewton meter, 31 kilonewton meter and 0 point. After marking these points, join this 0 to 15 straight line, that is a sloping line. Then 15 to 31 sloping line. Then join, close the polygon. This is the bending moment diagram for 2 point loads. It is negative. What we can observe here, see, wherever the point load occurs, that point this slope changes. Okay, this is the sloping line for the point loads. Okay, this is the 2 point loads we have considered. Let us see how bending moment and shear force diagram can be drawn for the 3 point loads. A cantilever beam 5 meter long. 5 meter long means 5 meter span from one point to another point, carries an point loads of 2 kilonewton, 3 kilonewton, 3 kilonewton at 1 meter, 3 meter, 5 meter from the fixed end. Now see, in this problem it is given distance from the fixed end. From the fixed end, 2 kilonewton is acting at a distance of 1 meter, 3 kilonewton is acting at a distance of 3 meter, and then another 3 kilonewton is acting at a distance of 5 meter from the fixed end. 1 meter from the one fixed end, 2 kilonewton is acting at a distance of 1 meter from the fixed end, 3 meter from the fixed end 3 kilonewton, another one is 5 meter from the fixed end. 5 meter means it is span also 5 meter and distance is given 5 meter. Therefore, this 3 kilonewton is acting at a distance of at free end. These are the 3 point loads considered. First problem we have considered the 1 point load. Second problem 2 point loads. Here another 1 point load is added. 3 point loads are there. To calculate the shear force at A. Okay, this is the point where vertical load is acting 3 kilonewton. Okay, shear force at A is equal to 3 kilonewton. It is positive because it is a downward force. Then shear force at B point, this 3 kilonewton plus another additional 3 kilonewton at the B. 3 plus 3, 6 kilonewton. Next, shear force at C. Whatever the 3 kilonewton here plus first point 3 kilonewton and then second point 3 kilonewton, then third point another 2 kilonewton is added. 3 plus 3 plus 2. 3 plus 3 plus 2, that is total 8 kilonewton. We can take previous value 6 plus another addition is 2. 8 kilonewton is the shear force at C. Let us see what is the value of D. Shear force at D. Shear force at D, in between the D to C, no load is added. Therefore, what is the value of the shear force at D? Is same as shear force at C. 3 plus 2 plus 3, 8, same 8 kilonewton value at the D. Maximum shear force occurs at the D point. Okay, like this we can calculate any number of point loads. We have to keep on adding the forces at that particular point. We will get the shear force. Then to calculate the bending moment. Bending moment at A. At A, since cantilever beam, at A is 0. Bending moment at B. What is the force? 3 kilonewton and distance from this point to this point. We are calculating the bending moment at B. Okay, 3 kilonewton into this distance, and which is the moment, clockwise moment. 3 into distance. What is the distance? 5 meter is the total span, and 3 meter from D to B. If you minus 5 minus 3, you will get a 2 here. Okay, that is 3 into 2. Minus 3 into 2 is equal to minus 6 kilonewton meter. This is the bending moment at B. Force into distance from the A point to B. Next, bending moment at C. To calculate bending moment at C, how to calculate? See, 3 is the kilonewton acting at free end, and distance from 3 to this point. That is, the distance is 5 meter minus 1 meter. This is the 1 meter from D to C, and 5 meter is the total span. 5 minus 1, that is 4 meter is the distance from A to C. Three into 4 meter, and then another force is acting here, 3 into this distance. To which point we are calculating? C point we are calculating the bending moment. Therefore, from the C, what is the distance of this this B point load at B, and what is the distance from C point to point load at A? This is the 3 kilonewton into distance is 4, and then 3 kilonewton into distance. Distance is 3 minus 1. Here 3 meter from D to B minus 1 meter from D to C. 3 minus 1, that is 2 meter. Minus 3 into 4, first point load, and second point load minus 3 into 2, that will be equal to minus 18 kilonewton meter bending moment at the C. To calculate the bending moment at D, we have to take the moment of all the we have to calculate the moment of all the forces at the D. This point we have to take the moment. How to take a moment? 3 into distance. 3 into distance. This 3 into this distance. This distance, 5 meter distance. Similarly, 3 into distance from B to D. 2 into distance from C to D. That distance is clearly here visible. 3 into 5 and then 3 into 3 and then 2 into 1. If you add all these 3 into 5, 3 into 3, 2 into 1, we will get the total moment at B. Here 3 into 5, 3 into 3, 2 into 1, 26 kilonewton meter is the bending moment at D, which is maximum. We can observe minimum bending moment is 0 at free end and maximum bending moment is 26 kilonewton meter at fixed end. Next, to draw the bending moment and shear force diagram, first draw the shear force diagram, draw horizontal line, then this is the point load, this shear force value is equal to 3 kilonewton, then horizontal line because no load is added between the A to B, then here 3 plus another 3 is added, 6 kilonewton, this vertical line should be equal to 3 kilonewton, then horizontal line, again here one more vertical line we have to draw because point load is there. What is the value of this vertical line? It should be equal to 2, that is 6 plus 2, 8, and then draw horizontal line because no load is added, shear force remains constant, close the polygon. This is the shear force diagram. Here one step, 1, 2, 3 steps are there because 3 point loads are acting. This is the shear force diagram. Next, to draw the bending moment diagram, first draw the horizontal line and mark the points. This point and B point you mark the draw the projection line and mark the points from C, from B, and here also draw the projection lines and mark the points at the B, C and D. (6 kilonewton meter at B, 18 kilonewton per meter at C, 26 kilonewton meter at the D. Then join this, join the lines. This closed polygon is called the bending moment diagram. Here we have to mark all the silent points what we are calculated. Negative. Okay, like this if it is given any number of point loads we can calculate the bending moment and shear force diagram easily. Now move on to the problem which is having an uniformly distributed load. This is the cantilever beam carrying an uniformly distributed load throughout its span. Span is 4 meter given and UDL is acting from A to B. Previous session I explained how to convert the UDL part to the point load. Let us see how to convert it. See this uniformly distributed load, if you want to convert into the equivalent point load, this is the 5 kilonewton per meter multiplied by 4 meter. It is a 5 kilonewton for every 1 meter it is acting. For 4 meter, 5 into 4, it is 20 kilonewton is acting at a distance of half. That is it exactly acts at the center. 4 meter means half is 2 meter. 2 meter from this A or 2 meter from the B. See 4 divided by 2. It is the 2 meter from the fixed end. Okay, whenever a UDL is given, that UDL its concentration will be at the center of its value, its whatever the length. Okay, and that we have to convert the point load by multiplying the distance up to which distance it is given. Now to calculate the shear force diagram, always it is not necessary to draw this simplified diagram. We can just we can understand in our mind itself it is acting like this. 5 into 4 is the total load and it is acting at center. We have to understand in our mind itself, we can calculate easily. But for basic level, it is better to convert into the point load and place it at the center of its distance. Now shear force at B. Now we can see if it is converted into the point load, definitely it is no load is acting at the B. Therefore shear force at B is equal to 0. Shear force at A. Here 2 points are there, one is B and another is A. Shear force at A, 5 into 4. Why it is 5 into 4? Because total load is acting from A to B is 5 into 4. That is 5 into 4, 20 kilonewton is acting. That is the shear force at A. Whenever UDL is given, that UDL has to be converted into the point load by multiplying its distance. Then bending moment at B. Bending moment at B, no load is acting, okay, therefore 0. Bending moment at A. Now you should be careful how we are calculated the bending moment at A. See what we can observe, 20 kilonewton is acting, that is 5 into 4. 5 into 4 is the 20 kilonewton is acting. What is the distance it is acting? 4 divided by 2, that is 2 meter. This distance from here to here distance is 2 meter. A to this central point. Therefore 5 into 4 into 4 by 2. 5 into 4 is the load acting. It is acting at a distance of 4 by 2, half of the distance. Therefore 40 kilonewton meter is the bending moment at the A. Bending moment at B is 0 and bending moment at A is maximum. And shear force at B is 0 and shear force at A is maximum 5 into 4, 20 kilonewton. Now to draw this shear force and bending moment diagram, you can observe here. First you draw the horizontal line and shear force at B is 0. Here it is the maximum. 0 is at 20 maximum, and then close the polygon. Here what we can observe, this bending moment diagram is sloping line. Sloping line because it is a UDL. Here 0 to it increases to 20. Whenever the UDL is given, that UDL point shear force diagram is sloping line. That means what we can say that whenever the point load occurs, that point load point, it will be equal to the that point load value, it drops. Whenever the UDL is given, that UDL portion it is inclined. Where no load is there, there is horizontal line. Next bending moment diagram, first draw the horizontal line and mark the point maximum bending moment at the support, this fixed end, and free end it is 0. Then you have to join by the curved line, parabolic line. This is not the straight line, it is a parabolic line. It should not be straight line. Wherever the uniformly distributed load is given, that then we have to draw the parabolic line in the bending moment diagram. Shear force diagram, it should be inclined line. This is the bending moment and shear force diagram for the beam carrying a uniformly distributed load. You should not draw the straight line when the UDL is given in case of bending moment diagram. Okay, this is the one simple case in which the uniformly distributed load is acting throughout its span. Let us consider next problem where uniformly distributed load is acting half the span. Say this is the beam, cantilever beam carrying an uniformly distributed load of half of its length. Okay, 4 meter is the total length and it is acting at a distance of 2 meter from the free end. From the free end it is 2 meter. Let us mark these points A, B and C. We have to find the bending moment and shear force values at the B, C and A. Shear force calculation. Shear force at B. What is the value of shear force at B? 0, because no load is acting at that point. It is 0. Shear force at C, this point total load is acting 5 into 2 meter. because it is a 5 kilonewton per meter. 1 meter it is 5 kilonewton, 2 meter it is a 5 into 2 10 kilonewton. Shear force at A, from the C to A no load is added, therefore it remains same. Whatever the 10 kilonewton previous value, same you can retain here at the A. Next, to calculate the bending moment at B, it is 0. For cantilever beam, bending moment will be always 0 at the support, at the free end, at the free end it is 0. Next, bending moment at C point, what is the load acting? 5 kilonewton into 2. 5 into 2 is the value. 5 into 2 is the value of load, and where it acts exactly at the center. It acts at the center. Vertical load, if we want to convert 5 into 2, that 10 kilonewton acts at the center of this length, 2 meter length. 2 divided by 2, that is 1 meter. Therefore 5 into 2 is the load which acts at the center of C to B, 1 meter from the C to this point. Therefore distance, force is acting at 1 meter from the C. Force is 20 kilonewton and acts at distance of 1 meter. Force into distance, that is the moment we are taking. This force into distance is 1 meter. Therefore 5 into 2 into 2 by 2, that is 10 kilonewton meter is the bending moment at C. To calculate bending moment at A, force into distance, that is force is 5 into 2, 10 kilonewton, and distance is, it is acting center of this point. From C to load point is 1 meter. 1 plus this 2 meter we have to add. That is the distance of force. UDL is acting at center. That center to the A point is 2 plus 2 by 2. 5 into 2 into 2 plus 2 by 2, that is 30 kilonewton meter is load, bending moment at A. That is the maximum bending moment at A. Like this, when UDL is given, UDL central point is calculated from the particular point where we require the moment. Next, to draw the shear force and bending moment diagram, as usual, draw horizontal line and then mark point, that is the 0 point. First point B, shear force is 0. Then inclined line. Why it is inclined line? Because it is a uniformly distributed load. For uniformly distributed load, we have to draw the inclined line, value of 10 kilonewton. Then again it is a horizontal line. No load is added between the A to C point. Then join. This is the shear force diagram for the uniformly distributed load acting half the span. If it is a half the span or whatever the distance UDL is acting, up to that distance we have to draw the inclined line, then it is horizontal line. This is the shear force diagram. Next, bending moment diagram. Draw first horizontal line, then mark the points. 10 kilonewton meter acting at this point. Project this, that point you mark the 10 kilonewton meter, then 30 kilonewton, mark 30 kilonewton meter, join this. What we can observe here, see, this is the point where 10 kilonewton meter bending moment, and from this point to C point to B point, it is a uniformly distributed load. That is why it is a parabolic, and after this point it is a straight line, inclined line, because from here to here bending moment changes from 10 to 30 kilonewton meter. This portion is parabolic, there UDL is acting. Inclined line and parabolic line you have to draw. This is the bending moment diagram for this particular beam. What we can observe here, we have to draw the parabolic line for the UDL uniformly distributed portion for the bending moment diagram. Now let us consider one more example where uniformly distributed load as well as point load, both are acting. See, this is the problem in which uniformly distributed load is acting from A to C, that is 2 meter distance from the fixed end. Previous problem we are consider the uniformly distributed load from the free end. Here we are consider the uniformly distributed load from the fixed end, and one more point load is acted at the free end. This is the point load. This problem consists of both uniformly distributed load as well as point load. This type of problem will be given for the examination normally, because you should know how to calculate the BMD SFT for both type of the cases. Shear force calculation. Shear force at B. At B, what is the load acting? It is the 3 kilonewton. It is a combination of first problem and whatever previous problem we have solved. Both we have to include here. At free end, it is a 3 kilonewton acting. Next, shear force at C. It is constant. You can see here from B to C, it's same. No other further load is added between the B to C. That is why it is a 3 kilonewton itself. Next, shear force at A. You can see 3 kilonewton is the previous value, this value, plus this load 5 kilonewton into 2. 5 kilonewton per meter is the uniformly distributed load. As I already explained, uniformly distributed load has to be converted into the point load. 5 into 2 10 kilonewton plus 3, total 13 kilonewton is the shear force at A. Whatever we are solving problem, we can observe all the places shear force is maximum at the fixed end. That is you have to observe. That is because all the loads are added together, and we can get the maximum shear force at the fixed end. For calculating the bending moment at B 0. For cantilever beam, always bending moment is 0 at free end. Bending moment at C point, you can observe 3 into 2. 3 into 2 is the distance. From C point to B point is distance is 2 meter, and 3 kilonewton is acting at the free end. This is the clockwise moment, that is why it is negative. 3 into 2 is the bending moment. 6 kilonewton meter is the bending moment at C. Bending moment at A. For calculating bending moment at A, 3 into distance is distance from B to A. Distance from B to A is 3 into 4. 3 into 4 minus 3 into 4 is the bending moment, and then this is the uniformly distributed load. For uniformly distributed load, 5 into 2 is the load, and then distance of the uniformly distributed load from the A is 2 divided by 2. That is 1 meter from the this point. The A to C, we have to place the point load at the center of this 2 meter. That is 2 by 2, 1 meter. Minus 3 into 4 minus 5 into 2 into 2 by 2. That is 22 kilonewton meter is the bending moment at A. Okay, now we will draw the shear force diagram. First, you draw the horizontal line. Then, what is the value? Without seeing the value itself, we can calculate here itself. 3 kilonewton is the shear force at this point, and also it is a vertical load acting. Point load is acting. Therefore, it should be vertical line here. 3 kilonewton. Then from here to here, there is no change of a shear force. Therefore, same 3 kilonewton remains same. And then for 5 into 2, 10 is added. Therefore, 10 plus 3, 13 kilonewton is the value at the A. Now, from what to do, it should be inclined line from here to here. Then there should be horizontal line, and we have to drop here, and we have to close this polygon. See, first vertical line, then is horizontal line, then inclined line, then we have to close. This is the uniformly distributed load acting. That is why it is a inclined line. then no load is there, horizontal line, and there point load is the vertical line. To draw the bending moment diagram, first draw the horizontal line, then these are the point. Starting here B point, it is a 0, then this here it is a 6, because 3 into 2, 6 kilonewton is the bending moment at this point, C point, and then A point 3 into 4 plus 5 into 2 into 2 by 2, that is 22 kilonewton meter is the bending moment at the A. Then join this inclined line, then it is a parabolic. From B to C is the inclined line, then it is a parabolic line because it is a uniformly distributed load. This is the bending moment diagram for the this particular diagram. Okay, in this case we have considered one point load and then uniformly distributed load half of the portion. Next let us take one more example where point load with uniformly distributed load throughout its length, one point load at free end, and UDL is acting from A to B. How to calculate the shear force and bending moment diagram for this particular case? Let us see. First shear force calculation, as usual, because it is a 3 kilonewton is acting at the free end, shear force at B will be 3 kilonewton itself. If it is a no point load is there, then shear force will be 0. Now here point load is there, that point load we have to consider for the shear force calculation. Then shear force at A, because only 2 points are there, one point is A and another is B. At A, to calculate A, 3 kilonewton, previous value 3 kilonewton, plus one more load is added, that is uniformly distributed load, which is acting 5 kilonewton per meter. 5 into 4, 20 kilonewton is the total load acting. 20 plus 3, 23 kilonewton is the total shear force at A. Next bending moment calculation. Bending moment at B. Bending moment for the cantilever beam at free end is 0. Therefore bending moment at B is 0. To calculate bending moment at A, this force 3 kilonewton into distance is 4 meter. 3 into 4. 3 into 4 is the moment of this point load. Then for uniformly distributed load, 5 into 4 is the total load, which acts at a distance of 2 meter from A, because it acts at the center. 5 into 4 is the load into distance is 4 by 2, 4 divided by 2. See here, minus 3 into 4 is the moment of point load, 3 into 4, then 5 into 4 is the load and distance is 4 divided by 2. If we add, we will get minus 52 kilonewton meter is the bending moment at A. Let us draw the bending moment and shear force and bending moment diagram. First draw horizontal line, then 3 kilonewton is the vertical load acting, vertical shear force, because load is acting 3 kilonewton, therefore it is a vertical line 3 kilonewton. Then what is the value, whatever the value here we have to draw here at A, and from here to here it should be inclined line. Why it is inclined line? Because it is a uniformly distributed load. Let us see how it looks like. See, this is the 23 kilonewton at A, 3 kilonewton at B. Then join this. Wherever uniform distributed load, we have to draw the inclined line in shear force diagram. You should be very careful when UDL is there. That UDL portion should be inclined line. This is the shear force diagram. Next, to draw the bending moment diagram, first draw the horizontal line. At B, it is a 0 value. Then at A it is a 52 kilonewton meter. From here to here we have to join by the parabolic, not straight line, since it is a UDL. This is the parabolic. So this is the bending moment diagram for this beam carrying an uniformly distributed load throughout its span and carrying a point load at the free end. Now let us take one more example, which is carrying in 2 point loads with uniformly distributed load. The half portion is acting with a uniformly distributed load 5 kilonewton per meter at a distance of up to distance of 2 meter from the A, and one point load is acting 3 kilonewton at free end. One more point load at a distance of 1 meter from the free end, that is 2 kilonewton. 2 point loads are taken and one UDL. To calculate this is we can observe here just again combination of point load and UDL. Just we have to add the point loads, and if it is UDL is there, that we have to multiply with the distance for calculating the shear force. Okay, this is the 1 meter is given. Okay, shear force at B. Shear force at B 3 kilonewton. How it is 3 kilonewton? Because 3 kilonewton is acting at the particular B point. Shear force at C. For calculating the shear force at C, 3 kilonewton already taken for calculation in previous B point. That 3 plus one more load is added, 2 kilonewton. 3 plus 2, 5 kilonewton is the shear force at C. Shear force at D. From D to C, no load is added, no further load is added. Therefore, 3 plus 2 is the 5 kilonewton is at D also same. Therefore, shear force remains constant from C to D. Shear force at A. At A, 3 kilonewton. 3 kilonewton, 3 kilonewton, then plus 2 kilonewton, 5 kilonewton, plus this one. This we should not add 5 kilonewton per meter. We have to add by 5 into 2 is the 10 kilonewton, plus 2 plus 3. That is 5 plus 5 into 2. 15 kilonewton is the total shear force at A. Maximum shear force at A. Bending moment. Bending moment at B, this point 0. Bending moment at C. C force is 3 kilonewton and acting at a distance of 1 meter from the C. 3 into distance is 1. Minus 3 kilonewton meter is the bending moment at C. Bending moment at D. Bending moment at D is force is 3 into distance is 2 meter. Force is 3 into 2 up to D point, it is a force 3 kilonewton is acting at a distance of 2 meter from the free end. 3 into 2 and then 2 into another one load is there, 2 into distance is 1 meter. 2 into 1. 3 into 2, 3 into 2, 2 into 1. That is 8 kilonewton meter bending moment at D. Bending moment at A. Now it is a complicated, you should be careful, because here we have to take the moment of UDL as well as point load. First we will take 3 kilonewton, which is taken moment towards the A. Distance is 2 plus 2, 2 plus 2, 4, 3 into 4, first load is over. Second load is 2 kilonewton and it is acting at a distance of 2 plus 1 meter, 3 meter, 2 into 3, 2 kilonewton into distance is 3 meter. Then third load is 5 kilonewton per meter into 2, that is 10 kilonewton point load, UDL converted to point load, into distance is 2 divided by 2. Center point is 2 divided by 2. This force into distance to A, and this force into distance to A, and this force into distance to A. That is 3 into distance, 2 into distance, and 5 kilonewton per meter into 2 into distance is 2 by 2. Like that, we have to take the moment of all the forces towards the A point to calculate the bending moment at A. 28 kilonewton meter is the bending moment at A. Let us draw the shear force and bending moment diagram. First draw the horizontal line, and then how this diagram will be. See, first 3 kilonewton is the vertical line, and then no load from here to here, horizontal line, and then 2 kilonewton is added. Here it is becomes a 5 kilonewton, and no further load is there. And then from D to A, it is a inclined line, and then join. That is where vertical line for point load. Here one more vertical line for point load. No load, horizontal line. No load, horizontal line, and then uniformly distributed load portion. We have to draw the inclined line. Okay, see, you can see this is the inclined line, and then this is the diagram. And then for bending moment diagram, you can say it is the inclined line, then inclined line, and then this portion parabolic. Inclined line, parabolic, both combination is there because it is a combination of point load and uniformly distributed load. See, by observing this step by step procedure, you can draw any type of the cantilever beam given with any load combinations. You can draw easily shear force and bending moment diagrams. Similarly, I have taken uniformly distributed load right side. See, you can observe shear force at uniformly distributed load right side, and one point load is acting at the end of the uniformly distributed load, and one more point load is acting here at 1 meter from this 3 kilonewton. Shear force at B is 0, B because no load is there, B is 0, and then shear force at C is 5 into 2 is load plus 3 kilonewton is added here, that is 13 kilonewton. Shear force at D 13 kilonewton, this value plus 2 kilonewton is added here, 15 kilonewton, and shear force at A, no further load is added, 15 kilonewton. Okay, that means here uniformly distributed load is considered here, plus we have added 2 kilonewton. Bending moment at B 0, bending moment at C, we have to take the moment 5 into 2 into 2 by 2. 5 into 2 is load into 2 by 2. Then bending moment at D, 5 into 2 is the load, plus 2 from here to here 1 meter is there, plus for 1 we have to add the half of this distance because it is acting at this center, minus this moment 3 into distance is 1 meter, 3 into 1 is the distance. Similarly, we can calculate bending moment at A, force into distance, this force into distance plus this distance, this 3 kilonewton into distance, 2 kilonewton into distance, we will get the 38 kilonewton meter. See, you can see here from B to C it is inclined line, and then here 3 kilonewton is dropped because of point load. Again it is a horizontal line, no load is added, and then vertical line, again it is a horizontal line, this is closed. Here it is a parabolic UDL portion, and then it is a inclined line. you should, wherever point load is there, we have to show the drop, and then UDL inclined line. Okay, this is the what we have studied the problem number 1 with only point load. Second is 2 point loads. Problem number 3 is 3 point loads. Problem number 4 is uniformly distributed load. Problem number 5 is half uniformly distributed load and 1 point load. Problem number 6 is uniformly distributed load right side, and then point load with uniformly distributed load. Problem 8 is 2 point loads and 1 uniformly distributed load, and here again UDL is shifted. These are the 9 problems we have discussed in this session. Okay, let us discuss in this in the next session. We will discuss about the simply supported beam, how to calculate the reactions and all. We will discuss in the next session. Thank you.